All right, hey, thanks everybody for joining us today. We have a really great webinar for you. We're going to be talking about lightweighting 3D printed injection mold tools to reduce cost and manufacturing time. We're really excited. I am representing from nTopology. Ben is representing from Fortify, and we're really excited to talk to you about this webinar. We have some really cool results to talk with you guys about. Quick little overview on who's talking to you guys today. My name is Evan Pills. I am from nTopology. I'm a senior application engineer. And what that means is I'm using nTopology, the software, 8-10 hours a day. I'm working with customers and clients and partners like Fortify, creating new workflows, really great case studies, and all these sorts of fantastic things. My background is mechanical engineering with a focus in additive manufacturing. So this is really kind of my foundation.
Hey guys, Ben McDonald here from Fortify, also an application engineer. I pretty much live in the injection molding world on a day-to-day basis, so everything from mold design, part design, all the way through molding parts, and really doing that with customers to show them how to use the Fortify technology to be successful.
Awesome. So let's dive in. Let's talk a little bit about what we're going to be talking about today. So quick, short agenda. We're going to start off with company introductions because there's no way everybody's familiar with both nTopology and Fortify. That'd be fantastic, but we're going to go over our companies just very briefly. Then we're going to dive into the workflow overview and the part creation in nTopology, because that's really where the story is going to start, is everything that I ended up doing to this part inside of the software. We're going to be talking about things like finite element analysis, field-driven design, reusable workflows. Then we'll dive into part creation and testing with Ben. He's going to do a fantastic job of telling you all about the actual printing on the Flux One, the torture testing that they put this through. He really did try to break this thing. And then we will go ahead and take a look at the results and do some questions at the very end. But that's kind of what we're looking like today. So quick background on nTopology. nTopology is a next generation engineering design software. What that means is we're looking to enable engineers to be able to design the things they always want to be able to design, what they actually want to be able to design at the end of the day. Right? We're not a CAD tool, we're a little bit different. We are an implicit modeling tool. So instead of representing things based off of the boundary like a typical CAD tool, right? Instead of faces and edges and points, we represent geometry based off of the entire design volume. It's a volumetric representation instead of a boundary representation. At a high level, that is the main difference, and it enables a lot of really fantastic, powerful things. And with this software that we've been developing with this volumetric representation and implicit modeling, we've seen a lot of fantastic success and growth over the past few years. And we attribute this success to three main things. The first being that implicit modeling technology that I'm talking about, right? Instead of that boundary, we're representing based off of that volume, which on the back end is stored as an implicit equation. So it's very lightweight, but it's also very robust and very reusable. So there's a lot of great things. You can do a lot more complexity than standard modeling tools. The second being field-driven design. And what I mean by that is I can take things like simulation data, like von Mises stress or velocity flow vectors, and I can use that data to influence parameters of my design. So now I'm coupling simulation and design into one to get the best geometries possible. And you'll see that later today. And the final are these reusable engineering workflows. And these are really the hidden gem of implicit modeling, because once you do the work once, you never have to do it again. So in this case, we're going to be going through these molds, variably shelling, variably infilling. And now that I have that all set up, we can just do it for any other mold that Fortify has. And I'll really show that to you guys once we get into the software.
All right, so Fortify, at our heart, we're a 3D printing company, but really what we're doing is some pretty next level stuff. So what Fortify does is we take, standard DLP printing. We take the benefits of that. So it's a scalable manufacturing platform, but it's also really limited on the kind of materials it can process. That's really due to viscosity ranges, chemistries, and things like that. So as a result, DLP in general, they can print a lot of these complex geometries, but they're not necessarily functional from an end user standpoint. So we take that DLP process and we combine that with polymer matrix composites. So these composites, they're really high performance materials, things like the RF market, chemical abrasion resistant, stuff like that. The downside of these materials is they're tough to manufacture. They're very, all those processes are super expensive, very complex, and the materials themselves are very expensive. So they're really great performing materials, but they're just not, they're so easy to manufacture. So what we do at Fortify is we combine the two. So we take, the additive manufacturing platform, the DLP, and we combine that with these composites to really print some high value production parts that are capable of doing things that, you don't really see in 3D printing or you haven't seen to this point.
Awesome. Well, with all that in mind, let's talk about the objectives of this, case study and this webinar that we're going through, because it's a pretty specific task that we're setting out to do. We're taking an injection mold from Fortify, their torture test injection mold, and we're going to be exploring that design space to try and minimize the mass while maintaining the structural integrity, right? As Ben can tell you, some of the main factors in creating these molds are the material use and the printing time. Right? And by reducing the mass, we're going to reduce the cost, and we're also going to get some benefits in the printing time that you'll see later. Right? We're going to be using field-driven design from FEA data in nTopology to actually create a variable shell and a variable lattice at the end of the day. We're going to be running verification analysis inside of nTopology, and we're going to ensure that those design criteria are met. And then finally, I'm going to send that over to Ben. He's going to print it, he's going to test it, and he's going to verify the simulation results and the design integrity. Right? So that's all our goals. Overall, the objectives are to remove as much material from this mold as possible while maintaining the structural integrity to keep the tolerances of the molding process in spec. Right? Overall, that is our goal. So let's talk about the workflow inside of nTopology itself. This is where we're going to start out. I'm going to give you a quick overview here, and then we're going to spend a lot of our time actually inside of nTopology. I'm going to be showing you the workflow, showing you the tool, and everything that happened inside of there. First thing I'm going to do is run a FEA analysis on the solid mold, the original body. I run that so I have my baseline, right? It's nothing special, but I need to know my displacements, my stresses. I like to have that baseline. The next thing I'm going to do is create a variable shell and a uniform infill, right? And I'll get into a lot more detail in this, but I'm going to variably shell my geometry, and I'm going to infill it with a uniform lattice, uniform unit cell size, uniform beam thickness. I'm going to take that, I'm going to run a FEA analysis on here. So I'm on the middle image here, give you a little circle here, I'm right here, variable shell and uniform infill FEA analysis. And the reason I'm doing this is I want the stress in the actual beams of the lattice structure, right? So instead of taking the stress analysis from the solid mold, I actually infill it and then take the stress in the beams themselves. So it's a little bit more of an accurate way to do this field-driven design. You can see we do have a stress concentration area here in our mold inside of the lattice structure itself. That's where the high stress in the beams are. So what I'm going to do is I'm going to take that data, and now I'm going to vary my infill. So where that stress is high, where this red is, I'm going to give it a thicker beam. And then the lattice is going to vary in thickness according to the actual simulation data here until it's down to the low values of stress and the thin beams. I'm going to take that, I'm going to run a variable shell and variable infill FEA analysis, verify my design, and I'm just going to rerun those final two steps, right? If I say, okay, my beams are too thin or too thick, I have too high of stress or displacement, whatever it is, I just get to change those values, right? And nTopology's reusable workflows allows it to just rerun and tell me if I'm right? So I can say, okay, this isn't thick enough, let me change it. So instead of 0.5, I'm going to go 0.6 or 0.7 or 0.8. And nTop just reruns and reruns and reruns until I hit my design goals, right? And that's a really fantastic part of those reusable workflows that we've been talking about. But instead of staying in slides the whole time, I definitely want to go ahead and hop into the tool. All right, so this is the tool. This is nTopology here, and we're going to be taking a look at the workflow that I put together to accomplish these goals, right? And you can see there's a couple of sections over here. We're going to go through pretty much all of them. We're going to start over here with the CAD, right? Because this is what Ben sent me at the beginning. He said, hey, this is what we're going to be working with. So all I ended up doing was taking this, importing it. You can see we have our Fortify mold. We have on the top, we have that knurling texture he's going to get into in the future. I'll zoom in a little bit so you guys can see that. But we have our initial mold imported into nTopology. And the first thing I'm going to do is take this, I'm going to do a little defeaturing. So I'm removing the wording on the bottom and other features that don't necessarily matter to the FEA analysis that I'm going to be doing, just to simplify the mesh, make things run a little bit quicker. Nothing special or fancy. And what I'm going to do for the remainder of this presentation in nTopology is I'm going to focus on what I call the upper here, because I'm actually looking at this upside down, but we're going to focus just on this body here, because everything I do to this body, I also do to the other body. So it'd be a bit redundant to show you guys both. But I'm also going to make a few selections. So I'm going to grab these two faces here. I'm going to grab these two. I'm going to grab the bottom. I'm I'm going to grab the top, and I'm grabbing all of these faces just with a couple selections here in nTop, specifically for that FEA that I've been talking about, right? So the first thing I'm going to do is I'm going to take my CAD, I'm going to take my selections, I'm going to go ahead and create a mesh. I create a mesh for the bottom and the top here. And what I'm going to do is run that initial FEA analysis that I talked about in my presentation. So I'm taking my upper here, I'm going to run it through the boundary conditions. I'm going to take my upper and I'm applying some fixed faces in some sides. I'll turn that mesh back on so you guys can see it. I'm going to apply some fixed faces on that side, on the tops and the bottom. And the way I'm restraining this is from right from Fortify, right from Ben. The faces are unable to move in the normal direction, but free in the other 2 degrees. Right, so in this case, the faces that I have highlighted, they cannot move in the X direction. Let me open that up for you guys. You can see there's no freedom in the X direction, but in the Y and the Z, it is free. But on these faces here, it's fixed in the Y direction, and in this bottom face, it's fixed in the Z direction, right? And that's enough for us to avoid rigid body motion. It's a well-posed problem for FEA. I can go ahead and throw a force on the top here, and we're actually designing to 10,000 pound force for the clamping force, right? And that's the standard that Fortify ends up using, so that's what we designed to. They do go higher than this in some rare instances, but 10,000 pound force is pretty common. So that's what we're designing to for this first case. Now, let me close a couple of things out over here and talk about what we did. The first thing we did, we went ahead and we ran the actual static analysis. So we have the stress, we have the von Mises, we have displacement, we have all of this data for both the top and the bottom, right? So we have all of that stress all through the thickness. And what I end up doing is taking that and pulling out my key values, right? And the key values here really are displacement. And you can see I have them highlighted over here in my notebook. The maximum upper displacement, which is what we're looking at right now, is 0.02 of an inch, 2.1, and the lower is 0.02 of an inch as well, right? So they're pretty spot on. They have really low displacement. And I actually know, thanks to Ben, that we can have around 0.10 of an inch of displacement, right? So that's kind of our limit. We don't want to go above that. So that's what we're going to be working towards, right? We have about 8 thou to work with, meaning we can remove some material from here, right? So the first thing I'm going to do is take my upper and I'm going to create, well, initially what I created. Initially what I created over here is a uniform shell. And you can see this is a uniform shell. It has 10 millimeters of shell thickness. And I started here because when discussing with Ben, we said we want a 10 millimeter wall thickness at least on the top, right? That's where we want, that's where all that clamping force is happening. We want that 10 millimeter wall thickness. So I started off with the uniform shell, but pretty quickly we were able to realize, that's not really a lot of room to work with. I actually ran an initial FEA on this and we found out, pretty much nothing changed. So what I ended up doing was taking this and instead creating a variable shell. So in this case, I'm tapering from 10 millimeters up at the top here, keeping that 10 millimeter wall thickness that we talked about. And I'm tapering all the way down to a 3 millimeter wall thickness at the bottom, because that's not where all the stresses and the forces are occurring. So we can really remove that extra material. And now we have a pretty large cavity to work with to, infill with the lattice structure to remove as much material as remove as much material as possible. Right. So what I'm going to do is take this cavity and I'm going to go ahead and start to infill it with this lattice structure here. Right. So let's focus up on just the lattice structure for a second. We have the lattice structure. I'm going to choose a couple of things. The first thing I need to choose is the unit cell, right? And I chose this body-centered cubic. And this was in conjunction with Fortify. We like this because of its completely self-supporting nature, right? There's nothing below a 45-degree overhang, so we're all completely self-supporting. I chose the unit cell size of 3 millimeters square, and the reason for that is because of the unsupported overhangs, right? So that's the largest unit cell we could do to really make sure this part is completely printable without any added supports. We didn't want to mess with that at all, so we chose that 3 millimeters. And the 0.5 millimeter beam thickness, I apply blanket to this part initially, and you can see they're all 0.5 millimeters here. That is chosen because that is the absolute smallest beam thickness that Fortify's Flex 1 machine can print. All right, so what we're trying to do is create the smallest lattice by volume to start off with, and that's what we've created. So now I have that inside of my shell. If we wanted to take all that, do another section cut, we definitely can go ahead and create a section cut. That's the wrong shell. We grab the variable shell there, right? So now we have this nice infilled variable shell with a uniform lattice. Now we have this initial design here right? What am I going to do? I'm going to take this and I need to run an FEA analysis on this, right? So the first thing I'm going to do, take my mesh here, my shell actually, and create a mesh for it. So let's take a look at this. We have some nice volumes, some nice elements through the volume here. It's a pretty good FEA quality mesh. And what I need to do is infill it with a lattice. Now, the reason the lattice looks like it does in not full solid tetrahedral elements is because I'm using a beam-based lattice FEA analysis. There's a reason for this, and let me swap back to the slides here. In nTopology, there are 3 ways we can run FEA on something like a lattice structure. The first being those completely solid tetrahedral elements, which is pretty standard. The second being beam-based elements, and the third being homogenization. Now, homogenization isn't going to work for us at the end of the day because in the end, we're going to be varying our lattice structure properties, so we can't really properly homogenize it. So we chose the beam-based elements. Why did I choose that? I chose that because there's a couple great things. If we take a look at this graph here, I'm comparing the 3 types to each other. The volume lattice and computation time for that simple one took about 300 seconds. The beam-based lattice took 1, right? It's an extremely fast computation time compared to these solid tetrahedral elements. And that is very important to me because I'm prototyping here. I'm working, I'm making changes. I want things to happen quickly. I don't want to have to wait 8 hours for an FEA to run. I want to wait 10 minutes for an FEA to run, right? The other being, it's a little bit inaccurate, right? So the volume lattice is saying our maximum stress is about 900 gigapascals here. This one is saying about 1400. So it's inaccurate, but its inaccuracy is overestimating instead of underestimating. So essentially, you'd be working with a built-in factor of safety at the end of the day. So this beam-based FEA analysis is going to speed up our time of creating this mold, but also still give us results that we're comfortable with, and we're going to test them and verify all this at the end. But that is why I'm choosing the beam-based elements as opposed to the solid tetrahedral elements in this case. So I'm going to take this, I'm going to join it all together, right? I'm going to grab some connectors. I'm going to tie this all together with some tie constraints here inside of nTop, and I'm going to run a static analysis here, right? So now I have the stress in my mold, the stress in my lattice, and let's focus in here. So let's see. I pulled out that same interesting parameter here, which is our maximum displacement. And you can see I have about 12 thousandths of an inch displacement with this lattice structure. So we're a little bit high. Right? We're a little bit high on our maximum displacement, but that is okay, right? We kind of anticipated that. We tried to create the absolute smallest lattice to begin with. And now what I can do is I can take not just all of the stress, but I can take the stress in the lattice structure itself and use it to vary parameters of the actual lattice structure now. So what I'm going to do is I'm going to take the stress where we have these high stresses, right? I'm going to have a thick lattice. Where I have these low stresses, I want a thin lattice, right? And I'm going to use that here in the next step where I'm creating the variable infilled upper, right? So the first thing I'm doing is I'm creating this variably thickened lattice. You can see it's happening here, but it's a little bit difficult to see in some cases. So what I'm going to do is I'm going to create this section cut. Let's take a look at it. You can sort of see we have some thicker beams over here and it's tapering over to some thinner beams over here. But let me overlay a nice view from our field viewing ability inside of nTop. Turn this on, and what we're seeing is the actual stress or the actual modifier we're using to change up our lattice structures, right? So as you remember in the last image, we had some high stresses over here, low stresses in other areas. If I probe some values, I'm now going from a 1 millimeter thick beam, according to where the high stresses are, and now I'm tapering my values according to the values of stress. So all the way over here in the light blues, I'm almost all the way back down to 0.5. And that's exactly what's happening. And I am in complete control of this in this little ramp here. So I'm saying at my high values of stress here, I want a 1 millimeter thick beam. At my low values of stress, I want a 0.5 millimeter thick beam, right? So now I am in complete control. The design engineer is in complete control of how I am varying this lattice structure. I create it, I put it back together with the shell. I go ahead and create another mesh with that lattice elements, the beam-based lattice elements and the solid tetrahedral mesh for the shell, and I run another verification analysis, right? We can look at our stresses, we can look at just the points in the lattice again. Now you can see things are distributed much more evenly. If we take a look at that same value here, the maximum displacement, now I'm at 9 thousandths of an inch of displacement, 9.6, if we want to get a little bit more specific, right? So we're below our tolerance level, right? We have hit our goal in this case, but I didn't hit this on my first try. Right? I absolutely did not get this on my first go. It looks all nice because I have this all finished up and I'm just showing it to you, right? But from 0.5 to 1, that was not my first choice. I actually started off from 0.5 to 0.6, and then I reran and I saw, well, I still have about 11.8 thousandths displacement, right? That's not quite good enough. So I just kept increasing this number. Everything in nTop reran for me, including this FEA verification, reran, just changed up this number until I hit 1, and I reached my goal here of below 10 thousandths of an inch of displacement. Right? So that's the value of those reusable workflows, especially when designing or exploring a design space like this, right? You don't have to redo any of the work along the way, even with something complex like a variable lattice structure inside of a variable shell and a FEA analysis with both tetrahedral and beam-based elements, right? All of that is able to rerun until I hit my goal. And on this upper that we're working on here, I actually get a 29% mass reduction, 29.04% mass reduction. Fantastic result there. And we're within our tolerances. So what I'm going to do is I'm going to turn this into a mesh, right? I'm going to take my final part here. Here's my infilled upper. It looks just like this. We put the words back on there. In the real one, right? I put the words back on there for them. But on the inside, if we take a look at the section cut, we have this nice variable lattice structure happening inside of there that, according to our FEA analysis, meets all of our design criteria. Right? Now that's fantastic. What I'm going to do, mesh it, send it over to Ben. He's going to print it out. But I did skip over all of the information for the lower. So let's quickly take a look at that, because the process was nearly identical. The first thing I did with the lower, I took that part, I created this shell, right? This is the upper here. I create the shell, but in this case, again, I start with the uniform shell. And in this case, we have some pillars that are running through. So they have that nice wall thickness happening as well. And the uniform shell, again, not quite good enough. We're going to switch. We're going to go over to this variable shell here. Right? Now we have some room to work with. So I'm going to go ahead and I'm going to put a lattice structure inside of there as well. I'm going to do all the same steps. I'm going to go ahead and create the mesh, and I'm going to run a static analysis on this part. We have stress, we have displacement, we have all those sorts of informations that we're looking at. And we find that with a variable shell and a uniform infill, we only have 7 thousandths of an inch of displacement. So on this one, I didn't even have to go place a variable lattice structure inside of there because of those pillars that you saw inside. We can just automatically say, okay, it's ready to go with that uniform infill. We can't make the infill any smaller. We know that because that's what we chose to do. So let's go ahead. Let's just print this one out as well. It's already meeting our criteria. So now we have two things, shelled and infilled. And if we take a look on the lower, we saved 23.83% mass, right? So even with just a uniform infill but a variable shell, we save a lot of mass as well. So I take these parts, mesh them, send them over to Ben, and now he can try to break them, right? All right. So let's hand it back to Ben. He can talk to you guys a little bit more.
All right, thanks, Evan. That was very insightful seeing that live demonstration. So let's dive into the Fortify platform. So before I print these parts, I'm going to give everyone a quick overview of exactly what we're going to be doing here. So the Fortify platform, we're combining hardware, software, and materials in order to print these high-performing injection molds in this case. So we have our Flex 1 3D printer. We pair that with our Compass software, and we use our digital tooling resin material in order to achieve these really nice results. So we pair this with two onboard modules that really enable us to do the printing of these high-performance parts. So the first one being our continuous kinetic mixing module. This allows us to suspend fibers within our resin in a homogeneous manner and then meter that resin throughout our reservoir so that we're always printing with good, low viscosity, evenly dispersed fibers in our material. So the second module on our printers is the flux print module. So this is really our secret sauce and something that really differentiates us from a lot of other printing companies out there. We have the ability to magnetically align particles that are within our resin. So in the case of our tooling resin, we're using a Z-axis alignment pattern, which is standard on all the Flux 1 machines, but that allows us to align our fibers in the Z-axis, and it really creates, some impressive parts, very good surface finish, all that good stuff. We pair all that with a really deep understanding of the applications that we're going after. So in this case, injection molding. We have brought in-house an injection molder that we're using day in and day out, print our tools, test them out, make changes, do all that great stuff. So what we found is that printed injection molds, they're just not quite the same as standard metal molds. You treat them a little differently, and they're going to treat you very well. So things like design, we're changing things like gating, venting, inserts, all that good stuff in order to optimize for our material. We do the same thing with our molding process. So we're changing our injection phase, our pack phase, our hold times, cooling times, all that good stuff so that we can really maximize the lifetime of our tools. With this particular tool here, this is our torture test. So we use this tool almost daily to learn about new, injection molding materials, new printing processes, refining printing processes, changing alignment patterns, all sorts of different stuff. And we're really pushing this tool to the limits to see what we can learn really. So our standard goal is 50 shots with this tool. And what we're going to count is actual feature failures on this tool. And that's going to tell us, hey, was this a good material? Was this a bad material? Good process, bad process. So some of the things we're looking at are like high aspect ratio pins. They're going to range from 1/2 degree of draft to 2 degrees of draft. We have a very tight knurling pattern that really helps us identify if our printing process is giving us good quality results. We have a shutoff feature that's really helping us test for tolerance. So if we're holding a good plus or minus 5 thou tolerance, more or less, whatever that might be. Then we have some other really challenging stuff like some close space ribs that all have 1/2 degree of draft and they vary in thickness, and blind pocket holes that are going to really be a test of pressure on this tool. So with that, let's get into what we actually did here. So with this tool, we took the STLs that Evan sent us and we printed them out, put them in our press, and we ran 50 parts. So some of the key parameters we were running with were 5 tons of clamp tonnage. That's kind of a standard value for us. And sometimes we'll go a little bit higher, but that's typically where we start with a mold. We're going 2,000 PSI injection pressure, 10 millimeters per second injection speed, 12,000 PSI, 1,200 PSI pack pressure. Those are kind of standard variables for us when we're running polypro, like we did with this mold here. So we ended up running our 50 shots. We had a handful of feature failures, which is right on par with what we would expect from a non-infilled tool. So if we jump to the results here, we found out that this infilled mold performed identically to our standard non-infilled molds. What do we gain? So we gain print time. Our standard mold tool is going to print in 8.5 hours, whereas this tool printed in only 6.5 hours. So 2 hours of savings. What does that actually mean? That means that we can print this tool and post-process this tool in the same day. So we're effectively saving ourselves 1 day on the prototyping process. Besides that, we are able to save, 100 milliliters of material. So that adds up to $60 in savings on resin, which if you're printing these molds day in and day out, that adds up very quickly. On top of that, it's just a really cool looking design.
I have to agree with you there, Ben. Definitely have to agree.
All right, with that, do you have anything else to add here, Evan?
Yeah, so I think the results that we got are fantastic, right? Especially that print time reduction and that extra day that we get in the prototyping speed. That really spoke to me when you told me that it printed it and was post processed the same day, because you normally said it takes 3, now it takes 2. That's pretty huge, especially with tight time frames and things like that. The material savings, $60, that is absolutely fantastic. It really lowers that barrier to entry on getting into these resin printed molds for low production runs or whatever it might be. So a lot of really great benefits, and the biggest one is now that we have this workflow established where we take your mold, we run it through the FEA, we do the variable shell, variable info, all that sort of stuff. It's already done in nTop. So now what we can do is we can take this workflow, take any other mold that you guys have, put it in there, and nTop will redo everything automatically for you. So now we can do this cost savings with very little overhead on the time it takes to create the new design as well. So there's a lot of really great benefits in this story here that I think would be fantastic for customers to really start to sink their teeth into. Right, they can really get a lot of benefit out of what we've done here today.
Pretty powerful stuff.
That's awesome.
So I think with that, we can open up to questions.
Absolutely, we're here, happy to sit here and take any questions you guys might have. If you put any in the Q&A chat along the way, we'll try and answer those first. But if you guys got questions, we'll answer them. Awesome. Awesome. Well, hey, thank you, everybody. We do see a couple of questions in chat so far. One says, "Hey, everyone, nice to meet you." Well, nice to meet you as well. Good. Thank you guys for joining. We really appreciate it. Let's see what else. We have a question here: is how do lattice structures affect shrinkage and warpage of parts? And that's a really good question. That's something that I think both Ben
Yeah.
and I can tackle, since Ben printed it and he would notice if there's any shrinkage. And personally, lattice structures, they do play an effect, but it's not usually a large effect. It usually is something you don't necessarily have to worry about. And on the scale of what we did in this case, we didn't have to think about that at all. Ben, is that correct?
That is correct. So with our particular material, we're seeing about a 0.5% shrinkage from a liquid state to a fully cured state. So there's not really a lot of shrinkage to take into consideration to start. Um, what it really is going to help with is just relieving any internal stresses that might be present during that shrinkage, which is not really a big consideration that we make either, because nothing we're printing is super massive. So it's really not a huge consideration for us.
Awesome. And Ben, I think we have another one
Yeah.
targeted towards you there.
So that's a good question. For this part, I would estimate on the order of about 50 shots before you're going to need to swap out that mold tool for something new. Um, it's tough to give a great answer off the top of my head for this part because it's very complex from a geometry standpoint. What we do have, and we're open to talking more about this on a separate call, but we have a calculator that we actually use to determine what kind of number of shots we can expect based on a given geometry and material. So to really give a solid answer, I'd have to run it through that calculator, but I imagine about 50 shots.
Awesome. And then same person asked, how much cost savings would there be if we count the design and FEA time? And the short of the answer is, on this first part, probably a little bit less, because it took me a little bit of time to design this workflow. But from any mold from here on out, this workflow exists. And what nTop will let you do is Fortify, if it's Ben doing it or anyone else at Fortify, they can bring in the mold, click on a couple of CAD faces, and everything will happen automatically. Right? So that design time will essentially go to zero, because yes, it might still take a few hours to process, but it's not hands-on anymore. And that's the really big thing. The design engineer can bring in the mold, click some CAD faces, hit run, come back in the morning or come back in the afternoon, and see if the goals were met, right? Or making just verifying things, and have the new design meshed and ready to go. So the cost savings would essentially still be the exact same because of that reusability factor that nTopology is enabling there. But that's a really fantastic question. Something I'm glad you asked for some clarification on, because I definitely didn't mention that in the actual presentation. I think that one's a question there for Ben.
Yeah, I mean, it seems like it's including design. So I guess we'll just go from starting a print to when we're ready to ship. So I think that's what we're asking here. But essentially, with the Fortify process, from pressing play on a print to being ready to ship, we're looking at about, I'd say, depending on the mold size, 2 to 3 days. So if you're going to be doing a mold on a similar size to what we did with this case study here, then you'd be looking at that 2-day example. No, yeah. And if it's a larger mold where print times are going to be longer, it might end up being on that 3-day range. But right in the 2 to 3 day range is how long it takes to start a print to have a mold that is ready to shoot parts with. And then you can tack on whatever shipping might be after that.
And there's a really good point that says, we can't see the questions. Can you read them before answering?
Oh man,
And
notice that.
that is we're a little rusty here. That's a good one. So that question that we just answered was, how much time is required to send a mold from USA to Germany, including the design time or without that design time. So what Ben was answering was, how fast of a turnaround can we, take in the parts that you want to mold and ship out the parts that have been molded. And to backtrack just a little bit and tell you guys some of the other questions really quickly. let's see here, is how do the lattice structures affect shrinkage and warping of parts? That was one of the first ones we answered. And the answer to that was essentially we didn't have to worry about it in this case due to the scale and the materials that we were printing out of. So we didn't really have to take that into account. In this case, though, if you get to a very, very large size of things, you'd want to run simulations on the shrinkage and warpage of the printed part. In resin, it's not as big of a deal. If you start printing in metal, then it's a big deal. The other one was how long would this tool last with 30% GF nylon? And the answer was
that was 50 shots.
50 shots. So that is a good answer because it didn't change too much. And the final question that we've answered so far is how much cost savings would there be if I count in the design time and the FEA time, right? And the answer was due to the reusability, we would have the same cost savings because now the barrier essentially doesn't exist. There's pretty much no added design time because everything happens automatically, right? So maybe a little bit of processing time, but actual hands-on time for the engineer, which drive up the costs, that doesn't happen anymore. So that gets lowered pretty well. All right. So Ben and I are happy to hang out and answer more questions if you guys happen to have them. So please, if you have questions, keep throwing them in the Q&A here. We will keep answering them. We've had 6 or 7 so far, which is fantastic. And we all are absolutely glad that you joined and asking questions. We love this sort of stuff. It's what we live for.
Okay, so the newest question here, what happens with the resin in between the lattice structure? Do you have any escape holes to drain it? So I actually did forget to mention this during the slides, but what I had to do is once Evan sent over those molds, I ended up making some cutouts on the back side of the mold itself to give resin a place to drain out of. But I assume you could probably do that with the nTop.
Yeah, we absolutely can. In the design time, the process itself, we somehow overlooked that. But yes, it would be about a 4-second operation to add in drain holes into the mold itself inside of nTop before creating that final mesh. Not an issue, not something that needs to be worried about or anything like that. It can absolutely be done right inside of nTop. We just overlooked it essentially at the end of the day. So yeah, Ben, you just go ahead and take and put some holes in there and let that drain. Didn't affect the performance or anything like that because we did it in an area of low stress. Didn't affect anything at the end of the day. But good question. Thank you for pointing out something that we overlooked there. Yeah, so good question is can this lattice structure be used as a cooling channel to get cycle time down? And that is something that Ben and I have actually discussed in the past is, hey, we've done this lightweighting one. What about decreasing cycle time with better cooling performance? And so this will be a bit of a joint answer. Can this lattice structure be used to get cycle time down? I don't believe we saw a reduction in cycle time with this lattice structure. Is that correct, Ben?
That's correct. So this structure was strictly about lightweighting. We didn't do any sort of active cooling through this lattice structure to help reduce cycle time. Where we'd really see a benefit from any sort of lattice structure is if it was really designed as more of a conformal cooling channel, something like that, as opposed to just a standard lattice. So we can really direct our cooling right underneath the surface of the part. The other flip side of that is with polymer-based tools, the thermal conductivity is pretty low. So the tool itself acts as somewhat of an insulator. So you're going to be able to get cycle times down with, designed in cooling channels, but it's not going to be as significant as if it were a metal tool. And you're going to see a lot more cycle time reduction with a metal tool as opposed to this.
Yep, and that's exactly what we discussed. So in the future, you may see another nTop Fortify, webinar collaboration where we do some conformal cooling channels inside of their molds. But as of right now, we did focus solely on the lightweighting, and we said, hey, maybe we'll see some cycle reduction just from doing this, and we didn't end up seeing any. But yeah, we focused just on the lightweighting in this case, which is fantastic. But lattice structures in general, this specific beam-based lattice structure wouldn't be optimal for increasing cooling performance. But inside of nTop, we create heat exchangers all the time. We help people with conformal cooling and molds and things like that, where we use more complex lattice structures with some more beneficial properties to them for increased cooling performance. Yeah. So another question came in, and thank you guys. You're asking a lot of questions. It's great. We love it. Does this practice translate to metal tooling as well? Do we know of any cases where lattice structures were successfully implemented into metal injection molding tool? And what I can say is yes, and that's about it. I can't really talk about that anymore, right? All that sort of NDAs and proprietary stuff. But yes, we've talked to a number of people who were interested in lightweighting their molding tools. Whether just to make it easier on the machine shop operators, right? Some metal injection molding tools get heavy, gets dangerous, reducing the cost because they're printing them anyway already due to the nature of some of what's going on or this or that. So yes, I have personally seen injection mold metal tools that have been lightweighted with lattice structures. Wonderful.
Okay, I'm gonna go ahead and take this one. So question we got here, is there a plan in the future to print out of steel or add a steel filler in the print material to help with cooling in a production tool? For Fortify, that's really not something we're focused on. We're really trying to go after prototyping space, low volume production. It's not really our goal to get into high volume production and stuff like that. And that's really where we'd see the biggest benefits with a steel filler. So whether you're looking at cooling or longevity of the tool, those aren't as big of consideration for the prototyping space. And we feel that our material as is a good candidate to solve challenges in that prototyping space. So short answer there is it's not really in our plans for the immediate future.
Question came in, and I can certainly take this one. Is you mentioned FEA, you used strut based model because of calculation time, but what if we use TPMS lattices? And for those who are unfamiliar, it is a surface based lattice instead of a beam based lattice, right? Is that method still applicable, or does it just take ages to simulate TPMS? And essentially, the method is not applicable, and it takes ages to simulate TPMS structures. Now, there are a couple more advanced techniques. You could use shell elements technically and things like that, but that level of advanced FEA doesn't exist directly inside of nTop. However, we could absolutely create those models and then send them to external tools potentially. There's some potential there, but the standard is more solid tetrahedral elements when you go towards TPMS structures. But no matter what you do, TPMS structures are so complicated and so complex to properly capture that calculation times are just always longer, essentially regardless of the method you use. So they're more difficult. That was one reason we didn't go that route, but the other being we wanted to remove as much material as possible, and the volume infill rate with something like a TPMS structure, I was assuming we'd have a little bit extra volume. We liked the beam-based lattice, the BCC, due to all of its self-supporting nature and everything like that. But you certainly could have used TPMS. It just would absolutely take longer to simulate at the end of the day. Not just to simulate, but just to mesh in general to get ready for the simulation. That would take quite a long time as well. All right. Well, it seems like questions are tapering off here. I think we've answered quite a few. I think Ben and I we're happy to sit here for another couple of minutes if any others do come in. But if they stop, I just want to give a preemptive thank you everybody for joining. We had a blast presenting to you guys today and answering your questions. And of course, if you have any further questions, you are more than welcome to reach out to Ben or myself or just Fortify or nTop. happy to get on calls, happy to discuss any questions you guys might have about the possibilities and what we can do. We'd love to have more conversations with you about anything that you're interested in. All right. Well, it looks like those questions are gonna come to an end here. So, one last thank you, everybody, and hopefully we'll see you at some of our future webinars.
Great. Thanks everyone for joining.
One more come in there.
Will the webinar be available on the website? That's a great question. It will be available, I believe, both on the Fortify and nTop website. So if you want to watch it again, any of that good stuff, it's going to be on the website.
Absolutely. Thanks, everybody. Have a fantastic holiday season, and everybody stay safe. Have a good time.
Yeah.
Cheers, everybody.
Thanks, everyone.